Namaste everyone. Today I am going to talk about one of the advanced technology in remote sensing that is called as hyperspectral remote sensing. So, simple dictionary meaning of remote sensing is what? That is collecting information without being in physical contact with the object. But hyperspectral, how it is different than our normal remote sensing, that I'll be discussing. So here you can see the word I written here is hyper and spectral. So hyper means what? Excessive. Means you have many, or you can say plenty of the things are there, and spectral is related to wavelength. So when you have excessive number of wavelengths used for remote sensing purposes, that is called as hyperspectral remote sensing. So here you can see one of the example of the data. This is called as one of the data cube generated from one of the airborne hyperspectral data, and the classification technique which you are going to see in this particular lecture will be different than your multispectral data classification. So before I talk about that, I'll be discussing that what are the important things which is most useful for remote sensing, and how hyperspectral remote sensing is advantageous for many of the applications. So in this slide, I'll be covering about data availability, that where you can get the data, what kind of data is there, the principle of hyperspectral remote sensing, then quality of the data, because when you have excessive number of bands, then the data quality is one of the major concern. So we have to go for pre-processing of the data. We have to remove the errors which is introduced due to sensor, due to your atmosphere or external parameter, and we have to convert that to surface reflectance. Then after that, we need to do the data dimensionality reduction, because what happens is when you have data, multiple data, and they are correlated with each other, then redundant data you should discard. So for doing that, you require data dimensionality reduction. After that, for classification, we require training signature selection from the data. In this case, the training signature selection will be termed as end member extraction. So either you can go to the ground, you have one of the instrument, that is spectroradiometer, correct the spectral reflectance curve of various features from the area, and then you can use that for identification and classification. Or from image itself, you should extract when the data is good, pure end members you can extract. You then use that for further classification and unmixing. So after that, you have to go for spectral mapping. You can generate unmixing, means in a single pixel how much fraction of the feature is present, that you can do. Later on, I'll be discussing about the enhancement of hyperspectral data, spatial enhancement, because what happens is your hyperspectral data, normally whatever is available, they are available with little bit coarser resolution. So how to enhance that, or if you want, you can integrate with other sensor data, that also I'll be discussing in this talk. So first, as I told, that two important things in remote sensing is what? First is spectral reflectance curve. If suppose you have to identify any feature from the Earth's surface using the remote sensing data, you should understand that how with wavelength the reflectance values varies. So you can see here in this particular curve, you have three major land cover features, that is dry soil, vegetation, and water. You can see water reflectance is very low. Your vegetation reflectance is, you can see it is high in green, dip in red, and very high in near infrared, and then it has dips in 1.4 and 1.9 micrometers, and little bit high in shortwave infrared also. If you see the nature of spectral reflectance curve of soil, it is increasing and constant throughout the wavelength region. So on the basis of that, you can majorly discriminate the three land cover features. But what happens when they have spectral similar materials? Like for example, you know when you have vegetation species you see all around, all will appear in green color, and in image, if you are interpreting standard false color composite, it will appear in red color, but they may be of different species. So if you have to differentiate the different species, you require the spectral reflectance curve should be in more detail. Like for example, you can see these two minerals are of iron, these two are the iron minerals, goethite and hematite. And you can see here the absorption present here and the steep slope is visible here is only differentiated when you have hyperspectral data. So normally what happens is on the basis of spectral resolution. So first important thing I talked about the spectral reflectance curve. Second important thing is resolution. So spectral resolution, on the basis of spectral resolution, your data set is categorized into three major categories, that is panchromatic, multispectral and hyperspectral. Panchromatic is considering broader spectral band which may cover visible region, entire visible region, or visible to near infrared region. In case of multispectral, the wavelength regions are divided and narrowed down to discrete wavelengths like blue, green, red, near infrared, and short wave infrared range. In case of hyperspectral, the bands are contiguous and it is covering the entire visible to reflected infrared. So, with the help of panchromatic band, normally we can differentiate features on the basis of grayscale, like water is darker, your urban features are brighter, vegetation are in gray color. But here, because it is a single band, you cannot generate color composite, differentiation is difficult. With multispectral band, it is little easy to differentiate the feature on the basis of color because the reflectance curve will be little better. But in case of hyperspectral, the reflectance curve will be in more detail. You can differentiate, like here you can see two iron minerals are there. Can differentiate it very clearly. So for that, how we are getting that many number of bands or hundreds of bands in hyperspectral data? So for that, you should understand spectral resolution. So normally spectral resolution definition is what? Ability of a system to discriminate two objects in terms of wavelength. And narrower the band intervals, the better is the spectral reflectance curve. So you see here how we can define that spectral reflectance resolution. So it is defined with the term that is called as full width half maximum. So here you can see this is the wavelength and this is the spectral response function. And when you are going to consider the full width of this spectral response curve and 50%, wherever 50% response is there and full width you are covering, so that is called as full width half maximum. So whatever wavelength range it is covering, that is called as the spectral resolution or bandwidth. And you can see here between two measurements of the detector, that is called as sampling interval. Now, how this spectral resolution is varying for panchromatic, multispectral, and hyperspectral? You see here. In this case, these are the spectral response function. In this black color, it is shown for the panchromatic wavelength range. And if you draw the full width half maximum, it will cover this much wavelength region. So this range will be, if you draw the full width half maximum, this range will be covered for your panchromatic. Now, in case of multispectral, you see it is having blue, green, red, and near infrared. And when you will draw the full width half maximum for this 50% response and this 50% response, this 50% response, so these are the discrete bands for this wavelength regions. Now, in this case, what is happening? For this blue band, you are going to get reflectance value, for green, for red, and near infrared. So you will have nature of the feature like spectral response reflectance curve of vegetation can be drawn, that vegetation have some value in blue, high in green, dip in red, and very high in near infrared. So by that way you can identify vegetation. But which vegetation species, it is going to be difficult. So in that case, you can see here hyperspectral bandwidth, how it will appear. So this is the spectral response function of one of the hyperspectral sensor. So the response function you can see when you will draw the full width half maximum between all the spectral response, you will see there will be no gap and it is going to be continuous, and for that you are going to get reflectance values. But if you see multispectral, you have for blue separately, green separately, red, and near infrared. So there are gaps in between also, but in this case you will have continuous data, so you will get continuous spectral information. So the detail of spectral reflectance curve are better in case of hyperspectral sensor. Now you can do the comparison between this. So here you can see this is the data in all the three data sets are in FCC. all mostly are appearing in similar color, because we can visualize only three color at it, three band at a time, because we have only three primary colors for visualization, that is red, green and blue. So when we have used six band for this in vegetation, you can see this is showing the nature of vegetation profile. When the number of band increased for this Earth observing one advanced land imagers sensor data, nine bands are there. Spectral reflectance curve is little more detailed. But in case of hyperspectral data, after 150 bands which left out after pre-processing, you can see the spectral reflectance curve is in more detail. So you can differentiate the species on the basis of this absorptions. So these absorptions are very, very narrow, that can only be detected when you have detailed number of, or you can say excessive number of bands for identification. So multispectral has discrete bands, hyperspectral normally has continuous bands. Now how we are getting this kind of this many number of bands, because for panchromatic the detector is single detector is there. If it is whisk broom scanner or push broom scanner, only one linear array of detector will be there. In case of multispectral, for different wavelength region different detectors will be there. But in case of hyperspectral, when you have hundreds of bands, and for that your number of detectors will be more, so it is quite a challenging task, because the weight of the sensor will increase. So in that case, what people started doing, they started using some different kind of technology for spectral separation. So you might have learned this exercise during your school time, that when you are using a prism and you are passing a monochromatic white light, spectral separation takes place. So similar kind of principle people used for doing the spectral separation and getting the different number of bands. And for that we are getting the reflectance values. So by that way they are doing the spectral separation. Now, normally, hyperspectral consists of many contiguous spectral bands, and ultimately it produces laboratory quality reflectance spectra when you convert that to surface reflectance. So what happens here is, let us say in this xy, xy is called as, you can say, as spatial information, and z is including the number of bands. So when you draw this as reflect curve, so for z you are drawing in the x axis, and in y axis you are drawing the values present in all the bands. So it will give you the spectral reflectance curve. So the hyperspectral data normally consists of 100 to 200 spectral bands, but nowadays spectral resolution are getting finer and finer. Now we have sensors which provides 425 or 30 bands also, and some sensors provide thousands of bands also. The ample spectral information provided by hyperspectral data is able to identify and distinguish spectral similar materials. So as I told, we can identify like different vegetation species with the help of hyperspectral data. Now let us discuss about this also. If suppose somebody says I have only 10 bands, and that is of 5 or 10 nanometer spectral resolution, can this will be called as can we call this as hyperspectral? Then yes, we can call that as hyperspectral. Let us say I am only talking about only a particular wavelength region, blue or green, and the spectral resolution is narrow, so that also comes under hyperspectral. But when you are going to cover entire wavelength region of optical, that is visible to reflected infrared, and that consists of hundreds or thousands of band, then that also comes under hyperspectral data. Now coming to the hyperspectral sensors. So, hyperspectral sensors are majorly categorized into three: airborne, spaceborne, and ground based. Airborne sensors are, there are many airborne sensors launched till date. From India also we have sensor like A-HIC, that is Indian technology. HiMap is there, Everest sensor is there, HiDice is there, digital airborne imaging spectrometer for Europe is there. And recently NASA and ISRO collaborated, and NASA JPL has developed a sensor, that is Everest next generation. So first Everest sensor was developed by NASA JPL during 1980s, And at that time they were able to get very they actually used that particular technology for mineral identification and mapping. Recently they modified and they upgraded the instrument, and earlier that was with 10 nanometer spectral resolution with 220 bands. Now this NASA JPL developed Everest next generation is with 5 nanometer spectral resolution, and number of bands are around 425. So ISRO and NASA collaborated. We have acquired data from various sites in India in two phases, and the data is available in the website which people can use for their applications and processing. Coming to spaceborne data, Hyperion is there, one of the popular sensor which was launched in 2000, and it was just following Landsat 1 minute behind Landsat, so that the data can be captured in the equal geometric, atmospheric and geometric condition. Compact high resolution imaging spectrometer is one of the sensor which is placed on Proba 1 satellite, and this particular sensor has capability of multi viewing, and it can view from 5 different angle, that is plus 55 degree, plus 36 degree, 0 degree, minus 36 degree, and minus 55 degree. Then HISIS was developed by ISRO, which was used for defense purpose. Prisma sensor was developed by Italian Space Agency. InMap is launched by German Space Agency recently. So these data sets are now available. Hyperion is now stopped working, but the data is available in the archive. Ground based instrument is one of the instrument that is called as spectroradiometer, which collect the spectral reflectance curve, and which is normally useful for measuring the spectral reflectance curve. We have now UAV hyperspectral sensors also, and they are very costly, but they can give you high spatial as well as spectral information. Coming to some of the future missions of hyperspectral, GISat is going to be launched from ISRO, that is with 320-meter. GISat means geostationary imaging satellite, which will be kept in geostationary platform, and it will look to the India and Asia Pacific region, so with VNIR with 320-meter and 192-meter in SWIR region spatial resolution. So coming to the other sensor, HISPRI is one of the sensor which is going to be launched by NASA, and this is having 60, going to have 60-meter resolution, but the swath width will be larger. In case of Hyperion, the swath width was very narrow, that was around 7.5 kilometer only. Coming to Hypersat is called as world's first commercial constellation of 6 high resolution hyperspectral imaging satellites, which will have 200 bands and sub 10 meter ground space resolution. So this is the details of the different airborne hyperspectral sensors. There are many more, so some of them I have listed. So this was the first hyperspectral sensor, one of the first hyperspectral sensor, but this geophysical environment research imaging spectrometer was affected by poor signal to noise ratio. The data quality was very bad. Then coming to Everest, so as I told, this was one of the major technological evolvement happened and used for mostly mineral identification and mapping. Then Canadian Space Agency developed compact airborne imaging spectrometer. Further, they developed the shortwave spectrographic imager also, and then thermal airborne spectrographic imager also. You can see for only till VNIR region, they have 288 bands. Then digital airborne imaging spectrometer is there. So in most of the cases you will see either it is covering visible to near infrared or visible to reflected infrared, and in some of the cases you will be seeing the gaps are also there. They are actually due to the in this particular wavelength region there is atmospheric absorptions. Then HiMap is developed by High Vista Corporation, and Spectre Group has developed AISA Eagle. So these some of the companies are there. Now they are developing the UAV hyperspectral sensors also. So this is one of the image taken from the NASA airborne Everest next generation sensor. So in this case, you see this is with 425 bands, 5 nanometer spectral resolution. In this case, the spatial resolution was around 5 meters, and spectral range is 375 to 2500 nanometer. Now you see here, this is the one of the image from Buxar area, that is Ganga river. Now you see The water quality, when the water is in the center part of the river, when it was taken, the reflectance was good, but there was drainage opening here, and because of this drainage, the contaminants which are getting added with this particular water, the reflectance went up. So we compared with our ground spectra also, so you can see here this result was quite comparable. So we can use this hyperspectral data for water quality analysis as well. Then coming to space-borne hyperspectral sensor, so MODIS normally we list that as hyperspectral sensor also, because they have from visible to near infrared to short wave infrared, we have 32 and 36 band. Then spatial resolution is varying from 2500 to 1000 meters. Maris is one of the sensor with 10 bands, but spectral resolution 15 bands, but 10 nanometer is the spectral resolution developed by European Space Agency. As I told, Hyperion was one of the sensor with good resolution 30 meter, but you can see here the swath width is only 7.5 kilometer. In this sensor, as I told, this is having multi-viewing capability and can see to a larger extent. Then HIC is one of the sensor on IMS-1, that is Indian Mini Satellite 1. Similar sensor was flown with Chandrayaan 1 satellite. Then HISIS is developed by ISRO, launched in November 2018. Prisma was launched in 2019 from Italian Space Agency, and INMAP is launched by German Space Agency in 2022. Then coming to extra terrestrial hyperspectral sensors, so Chandrayaan 1 high C, Chandrayaan 1 mineralogical mapper, Omega is there. Then CRISM is one of the sensor in Mars reconnaissance orbiter. Thermal imaging sensor is there. Chandrayaan 2 was also having one of the hyperspectral sensor. So this is one of the Hyperion sensor specifications. So as I told, the EO1 satellite was following 1 minute behind Landsat 7 to collect the data with the similar atmospheric condition. 220 bands are the having the spectral bands. 0.4 to 2.5 micrometer is the spectral range, and 30 meter is the spatial resolution. Swath width 7.5 kilometer. So this is one of the Hyperion sensor, and this is the data Hyperion data of the Rishikesh area. So this area image, the subsetted part of this area image, I have shown you in the earlier image. This is one of the HISIS sensor launched from ISRO. So the spectra of different locations are shown in this particular image. And you see here, it is ranging from 400 to 2500 nanometer. And normally what happens in hyperspectral is the detectors for VNIR and short wave infrared range are different. So there are chances of overlap also, like 400 to 950, and in SWIR it is starting from 850 to 2500 nanometers. Spatial resolution is 30 meter and swath width is 30 kilometers. Then coming to Prisma sensor. So this is the Prisma sensor of Dehradun area, and you can see 30-meter spatial resolution, 30 kilometer swath width, and the spectral resolution is less than 12 nanometer, ranging from 400 to around 2500 nanometers. These are future missions of hyperspectral, which are, will come in upcoming future. As I told, this high speed is developed by NASA from 380 to 2500 nanometer, 60-meter resolution, and 145 kilometers swath width. Now coming to the quality of the data, data quality, actually why we have to take care, because when there is a spatial noise, it hampers only the visual interpretation. But when there will be spectral noise, what happens is the absorption of the particular bands are actually getting affected, and you cannot identify the features clearly. So because in hyperspectral, absorption is one of the important factor, which tells that this is this material or this is whatever material it is. So by looking over the absorption, we can identify easily. So the sources of noise are what? Normally sensor drift, means sensor quality changes with time. Then signal conversion, when it is converted from analog to digital, like radians to digital number value, then some noise can add. Electronic vibrations and moving parts in the sensor can also affect the signal. Platforms vibrations, and especially aircraft engine, if it is flying in the airborne sensor, so that is affecting the data. Then irradiance variation, because radiance energy is also varying from morning to evening. Then from different weather condition also, means like summer, winter or spring season, when you will acquire data on monsoon season, the data will be affected by your solar illumination, aerosols and water vapor. Atmospheric attenuation takes place because atmosphere has different layers. So whatever energy we are expecting to receive, some are getting scattered, some are getting absorbed, so that is also affecting. And because of that, path radiance also happens, which causes haze error also. Then how to correct this kind of errors which get introduced? So if suppose it is introduced due to sensor, like sensor introduced error, how it looks like. So you can see, as I told, 220 bands are getting captured by your hyperspectral sensor. So but as I told, VNIR and SWIR, two detectors are there, so there are some overlap between, so that's why there are 242 bands when you will download from the website. Now, what happens is, when you will open the data, you will see that the initial bands, the bands which are at the 2500 nanometer, and the bands which is in the atmospheric absorption region, they contain no values or noisy values. So these bands are of no use, you have to discard. Then some of the bands will have this drop line error. So this drop line error, how we'll correct? So this band which is of having no information, you should remove it. Or if you have this drop line errors, so you pass a mean kernel from all over the image, it can get corrected. Or third technique is minimum noise fraction. So in this we can reduce the noise to a larger extent. So this I'll be discussing in data dimensionality reduction also. So this is one of the technique which also do the noise reduction, as well as it will do the data dimensionality reduction. Now, this is the entire process of your hyperspectral data. Normally, when you will download the data will be in radiance form. First, you do the sensor error correction. After that, you should go for atmospheric correction. Now, after atmospheric correction, you will convert that to reflectance, because we require the data should be in surface reflectance form. Then only we can identify which feature is what. After that, you can go for data dimensionality reduction, and you can use either the spectral library, or you extract the end members from the data. After extracting end members, you can get this kind of data, and use this end member or spectral library with the data, you can generate a classified map. So for that, how to convert that data to surface reflectance? So for that, we should go for atmospheric correction. For that also, you have different approaches, that is relative as well as absolute approach. In case of relative approach, what happens is, you have data and you don't have any parameter and you need to convert. So image, this is image based method only. What you have to do, like simplest technique, simplest one, I'll be explaining, like flat field is there. So for converting the data to reflectance, you require two measurements, radiance and irradiance. But radiance is there, we don't have irradiance. So what we are doing is, we have to identify some of the features which are having highest reflectance, like bare field is there. Take the average pixel value of this bare field, divide from each and every pixel. That is called as flat field. In case of IRR, internal average relative reflectance, in this case, consider the whole image, take the average pixel value of whole image, divide from each and every pixel. That is called as IRR technique. In case of empirical line, you need measurements of two objects, darker and bright, and then you have to develop a kind of regression line between the data to your the output, and you have to generate constants, and through that you can convert that to surface reflectance. So this is one of the relative method. In case of atmospheric model which generates absolute reflectance, that is based on radiative transfer model, and in this case you require several parameters. Several parameters, like you require atmospheric condition, water vapor condition, you require aerosol level, water vapor, you require the date and time of acquisition, the geometry of the data, sun angle, solar azimuth. So various parameters are required. You have to substitute this parameter, and then you will be able to convert that to surface reflectance. So flash is one of the technique that is fast line of analysis of atmospheric spectral hypercubes. ATREM is atmospheric removal, and ATCORE is one of the technique which is available with two versions, ATCORE 2 and ATCORE 3. ATCORE 2 works when the area is flat. ATCORE 3 is one of the technique which uses digital elevation model for correcting, because your earth surface is not flat, it is having undulations. So while doing the proper correction, you require one of the external parameter, that is digital terrain model, for proper atmospheric correction. So after atmospheric correction, you see this is the radiance spectral profile, and after that you can see the urban feature nature of spectral profile is coming similar. This is one of the example again. This is of Hyperion sensor data. So I have shown vegetation profile, your dry river profile, and water profile, how it is coming after atmospheric correction. Then we can go for geometric processing. Why we have to go for geometric processing? So once the data is acquired, you see here, when there is an undulation, the pixel size is different, which is acquired. The location error is also coming when there is undulation. So normally when you have to go for correction, either we do only geocorrected with the help of GPS aircraft altitude, and provide the coordinates. So that is one of the way, that is called as simple geocoding. But normally the surface is not, when there is a flat surface, this the data will be fine. But when there is undulation and you are using digital terrain model to properly geo-rectify the data, so GPS, aircraft altitude, and topography is considered, then that is a proper orthorectified image, which is the coordinates are at the proper locations. So this is required to be done. Nowadays people are providing data, level 2 data, which is geotiff, that is orthorectified images also. Now coming to the data dimensionality reduction, why we need to go for data dimensionality reduction. So what happens is, as I told, the dimensionality reduction is necessary when you have to subset spectrum of interest. You have to reduce computational overhead. Means when you have two hundreds of bands and you will apply processing, or you which is containing 100% of information, and when you have 10 bands out of 200 bands and containing 90% of information or 95% of information with reduced noise, then it will take less time to process. And in this case, this reduced noise also improve SNR of the data also. So some of the techniques are principal component analysis, minimum noise fraction, and independent component analysis. So you see here, PCA is what? So this is one of the data dimensionality reduction technique. In this case, what happens is, as I told, we are converting, or we are translating and rotating our data as such. In the maximum variance of the data is coming into the newer components. So first component contains maximum of the information, then second, and when it reaches in the increasing the number of components, the noise content will come into picture. But in case of hyperspectral data, in case of my multispectral data, this trend will be followed. But in case of hyperspectral data, this trend will not be followed, because what happens that in hyperspectral data, the data is very, the bands are very narrow, so it includes, even after pre-processing, it includes some of the noise content also some of the time. So what happens will, in this case, you see the PCA 1, 2, 3, 4 are informative, fifth is informative, all of a sudden sixth is noisy, then seventh is informative, then eighth is also little bit of information is there. So in between that, noisy component will come. But why it is happening? Because when we are translating and rotating, we are not bothered about the noise content present in the data. So in that case, we are applying another technique that is called as minimum noise fraction. And in this case, the name itself says minimum noise fraction. So we are applying a principal component analysis twice. How? In first step, what it does is, Like we know we are applying a method that is called as shift difference. So we have, neighboring pixels normally contains similar kind of values, but similar signals, but noise content may vary. So the shift difference means method means what? We are shifting the adjacent pixels and calculating the differences between the adjacent pixels. So because of that differences, the noise amount will be calculated and the data will be uh, generated as noise reduced data. After that, we are applying PCA to transform and rotate to generate the components which are noise reduced, as well as redundant data are also reduced. So here you see the trend is now followed. So in between that, there is no reduction or no noisy component coming in between. Then coming to independent component analysis, this is one of the data dimensionality reduction technique where people are means in this case, like for example, you can compare with this. We are trying to separate out individual signal or independent signals from the data. So this uses higher order statistics like skewness and kurtosis. And with a simple example, you can compare, like you are listening to music, and if you listen to the music carefully, you will be able to separate out the sounds coming from the different particular musical instruments. So that independent signals are separated if you listen to the song carefully. So here also, and because the sounds are intermixed, in this case also the signals are intermixed and they are very narrow. Using the higher order statistics, you can differentiate different features. So here you can see the features which are different are identified in different components in this image. Now coming to the next step, that I told that in case of multispectral data classification, we term that as training signature selection. So here this is termed as end member extraction. So how we do the end member extraction? Either you go to the field, create your own field or lab measurements using spectroradiometer. Like here you can see this spectroradiometer is here, and how is collecting the spectral data. Then you can use the publicly available spectral library, like uh, NV software has publicly available spectral library. Speclib.jpl.nasa.gov has spectral library generated from various features. Or the steps from the image, if you have to extract n members, these steps needs to be followed, that is MNF, PPI and ND visualizer. So this is the spectra collected from this spectroradiometer. These steps I'll be telling you further. So how we can collect spectral data using spectroradiometer? So normally you should start the instrument half an hour before, and the instrument should be charged, fully charged, before you are going to take to the for the data collection. Then there are three steps to measure: dark current measurement, white reference measurement, and target measurement. In case of dark current, because what happens is, even after you will not use any electronic device, some electric current is flowing inside it. So that is treated as kind of some measurement which may get added to the measurement of your target. So this needs to be removed. Then after, you can go for white reference measurement, that is, you can say you are doing the calibration, or you can say this is a baseline. And after that, when you are going to do the target measurement, so this will give you the reflectance curves. So here you can see how the reflectance curve coming from this instrument, and this particular wavelength regions, you can see this is having atmospheric absorptions. Now after that, if suppose you don't have spectroradiometer and from image you have to collect the end member, then you can have to go for two major steps, that is pixel purity index and ND visualizer. Pixel purity index we have to do to identify most spectrally pure pixel location from all around the image, and those pure pixels which are identified, we have to put in ND visualizer, and we have to translate, rotate and move as such that whatever pixels are coming at the extreme, we have to extract that as pure end members. So these end members are identified. Then we can go from whatever locations they are identified. You can see these are the pixels which were extracted after rotating and translated, and these are will be formed in form of ROI or in form of your spectral libraries. So use these spectral libraries and then you use for identification and classification. Now suppose we have extracted end members, but we don't know what this end member is or what feature is this. So you can go to the field, you can note, you can check what features are present in this particular end member, and you can note down if you don't have spectroradiometer, and then you can use it for identification and classification of the material all around the area. Then coming to the classification of hyperspectral data. So we have many classification techniques. Some of them I am explaining. One of the technique is spectral angle mapper, spectral feature fitting, linear spectral unmixing, and mixture tune match filtering. These last two techniques are actually, you can say, sub-pixel classification techniques are there. We can where we can tell the weighted fractional coefficient of the features present. So first, SAM classification, how it works. So normally in this case you require two measurements, reference and your image spectra. So reference spectrum is called as ASD spectrum also, because some in earlier days the spectroradiometer which was invented was with ASD spectroradiometer. So the format is ASD. So or you can use it from other spectroradiometer also. They will be called as reference spectra. So you have to do the spectral similarity between two you with the help of the spectral angle between the image and reference spectra. So let us say this is the spectral reflectance of object R, this is reference spectra, and this is the image spectra that is represented in form of vector. Now what happens is in this is the minimum the angle, better is the match. So here you can see two spec objects are there, T and K. When we tried to match, whichever gave minimum angle, it went to the classification. Now this particular classification technique is has one more advantage, that is what, if suppose same feature is there, okay, but it is one is in the brighter side, another is in the shaded side. So what happens is the direction of vector will play a role, not the magnitude. Means the feature which is in the lowest in the shaded side will have lower magnitude, the feature will have the highest means brighter which is in the illuminated side will have highest magnitude. So whatever features are there, because the reflectance curve will be of similar nature, absorption positions will be in the same wavelength position, so they may have high or low reflectance, but it will lie in the same vector, so it will go to the same class. So this technique is insensitive to illumination variation. Like here you can see there is a variation in the illumination. When we use maximum likelihood classifier, you can see it is not classified properly, but with the help of SAM it classified properly. So in this you can generate two types of output, one colorful classified output and ruled images for whatever end members you give. So in this case you can say darker pixels more similar. So you can see grassland, wherever grassland is there it is darker, wherever urban area is there it is darker. So different ruled images for different end members whatever you give, and darker pixels more similar. So this is one of the you can say the FCC image of Everest, and when the angle was taken very less, fewer pixels classified. You increase it to 0.05, some pixels got classified, some more pixels. When you increase it to 0.1 radians, maximum pixel got classified, but some are remain unclassified, even or some are showing misclassification also. Greater than 0.1 radians, you can see misclassification started occurring. This is one of the example of your multispectral and hyperspectral classified data. You see in this case there are some of the classes which are misclassified in this multispectral data, but here this classification got improved and species level classification we can do. Now coming to spectral feature fitting. So as I told, in case of hyperspectral data, absorption features are important. So here what we have to do is we have to first isolate the absorption feature in a common baseline. Then we can measure the depth and measure the shape, and you just match with the image spectra with your reference spectra, the depth and shape. Once it will match, it will go to that class. So here you can see this is the root mean square image for alunite. Wherever alunite is there, the brighter pixels are considered as more matching is present here. So, in only spectral angle mapper, darker pixels are more similar. In other cases, brighter pixels are the more similar pixels which are coming as output. Now, in this case, what we did was we classified the data with the help of pixel based approach and object based approach. So, with the help of pixel based approach, you can see wherever the gaps are there or in between the other things are there. So, it was misclassifying or not classifying properly. But with the help of object based classification, we gave certain criterias with the help of indices generation, shape, and other texture parameters we considered, and when we gave that, we are able to classify the features more clearly. Then, sometimes we are seeing confusion between in some classes, like here you see water is there and shadow is there of some building, so they are having normally similar reflectance curve. In case of concrete and GIC, they are also having similar spectral reflectance. But in this case, what we did was we integrated thermal data and the temperature was different. When we integrated the thermal data by doing rule based classification, we are able to improvise the classification. So here this is one of the Sabarmati riverfront which was made with concrete mostly, and here it was going as GIC. So this went improved because of the temperature difference. And here also in this case you can see the asphalt was going or misclassified as water pixels. That also further improved with the help of thermal data. Now coming to spectral mixing for a single pixel, how we can identify what feature is present in the hyperspectral data. So hyperspectral data has that advantage. So normally mixing is of two major categories, linear and non-linear. Linear mixtures are what, like energy is coming and separately it is going to the sensor. And non-linear is when you have kind of non-linear mixture or intimate mixtures are there. So the combined response from the object will go, and it is difficult to differentiate linearly. So but it is able to tell that how much percentage of that feature is present. How? Let us say we have three objects A, B and C, and this is A, this is B and this is C. So in this area the dominance of C will be there, dominance of A will be there, and dominance of B will be there. Mixing space is this. So what happens if you see the reflectance curve of A, reflectance curve of B, reflectance curve of C, the absorption positions are lying at different wavelengths. Now when we combine, we'll get the combined response of this pixel. You will get the reflectance curve like this, which will have all the three absorptions present, as well as whichever feature has more contribution will have higher or the absorption is more dominant in that case. So to differentiate this three, we can generate abundance images or weighted fractional coefficient images by giving the n numbers. So let us say when we give water, wherever water is there, that got highlighted, rest of the features are suppressed. Wherever scrubs are there, they got highlighted, rest of the things are suppressed. So it means this brighter pixels means represent, in this case you have higher number, or you can say the weighted fractional value of that feature is more in this particular abundance images. Now coming to the another technique that is called as mixture tune match filtering. In case of linear spectral unmixing, we have to give all the n members present in the area and it will generate that many number of output. But suppose I am not bothered about all the information present in the data. Let us say I am only bothered about the urban area, or I am bothered about the vegetation areas. Then what we can do, this particular technique will be called as partial unmixing, and the name itself says first is matched filtering, means whatever end member you will give, wherever that end member is present it will be highlighted and rest of the thing will be suppressed. And mixture tune means what, in match filtering there are chances of creating confusion between similar classes, like let us say urban and dry riverbed. So because the material are similar they may create confusion, like in this case both urban and dry riverbed were bright, but when we use in mixture tune mass filtering, an additional output was generated that is called as invisibility image. So in score it is high and invisibility value should be low. then it will be treated as only that feature. So wherever urban is there, you see I have considered high score and low invisibility value. So urban is coming as is highlighted with this red color. In this case also, high score low invisibility we took, that vegetation feature is highlighted. Now in this image also you can see this is your vegetation, and this is your score image and invisibility image. Score image will be more values, and invisibility value will have darker value for the same feature. Now, as I told that we can do the enhancement of hyperspectral data. So enhancement we can do by two ways. One, either you go for super resolution. So in this we have used single frame super resolution technique. So here you can see with this single frame super resolution, this is your nearest neighbor resample data. The data is available with 8-meter resolution. So when we only did resampling, you see the shape of the features, the edges of the buildings are not clear. But when we did the super resolution and generated from 8-meter to 4-meter, you see that vegetation in this area, the road edges and the building edges are more clear. So the shape of those things can be clearly demarcated. And when we did the classification, there were certain confusions also coming when we did when the nearest neighbor resampled. The soil was going as China mosaic, but when we use the super resolved data, it was classified in form of this soil only. Then coming to when you can do the fusion with panchromatic data. So this is Hyperion data with 19 spectral bands and spectral profile you can see. But if you see the shape of the this building, this is little distorted or blurred. But when we fuse with panchromatic data, which is present in EO1 satellite advanced land imager, and because there the wavelength range, common wavelength range was taken for fusion, which is with only which is giving only 19 bands from hyperspectral. When we fuse that, it preserves the spectral reflectance values, and the shape of the building material was better, is better compared to your this hyperspectral data. Then we can integrate data with SAR images also. So we did pixel label feature label fusion with C band and L band data, and we found that feature label fusion was giving better result, as well as decision label fusion is also giving good result compared to your pixel label fusion and your normal hyperspectral data. Now coming to the applications of hyperspectral data, we can use it for various applications like vegetation, soil studies, mineral mapping, water quality, snow grain size, and urban studies. So here you can see for vegetation species mapping, when we compared with ETM plus and ALI and Hyperion data with 6 band, 9 band, and around 150 bands, the accuracy coming was 85.71% in case of Hyperion. And species level classification was possible and better compared to this multispectral data sets. So how it is possible, you can see through this images. In this you can see the spectral reflectance curve are coming as more or less similar. And here in case of hyperspectral, we highlighted certain wavelength ranges to see whether there is variation between the spectra of different features or not. And we can clearly see there is difference, and because of that the species level classification was possible in Hyperion data. Now coming to the soil studies. So for soil studies, we can classify different types of soil. If soil is getting added with moisture, wet soil, dry soil classification, or different organic content variation is there, then also you can use this hyperspectral data. Soil salinity analysis you can do through this hyperspectral data. So here we tried to classify red soil and black soil with the help of reflectance data and with the help of MNF based component data. So in this case, there was confusion between red soil and black soil was overly classified. But when we use this MNF component data for classification, red soil and black soil got classified properly. Then we can use this data for mineral identification and mapping. Here I have used compact airborne spectrographic imager, shortwave airborne spectrographic imager, and IIRS NG data for identifying where which minerals are there. So this is showing the alunite abundance image, carbonate abundance image, and dikite and smectite abundance image. And in case of compact airborne spectrographic imager, because it is covering only visible to near infrared, so iron bearing minerals can be mapped. And in every SNG, because it is considering complete wavelength region from visible to reflected infrared, all the minerals got classified. In short wave infrared, apart from iron mineral, other minerals got classified properly. Then I told that we can use this for water quality study. So we have used here hyperspectral data during the Everest NG data collection. So we went to the field, we collected spectral reflectance curve through spectroradiometer, and from the same locations, we the spectra we also collected with the help of turbidity meter. We measured the turbidity of the particular water locations. So when we classified that, we are able to different did do the classification of different turbidity level, and we classified the water quality in this with the help of what hyperspectral data. And when we matched with the turbidity meter data, it was coming more or less similar. Then we can go for snow grain size mapping. You can see here medium grain, fine grain, and coarser grain snow can also be classified with the help of hyperspectral data. As with different type of different grain size snow, the spectra is also varying. Then we can do the urban material identification mapping with the help of hyperspectral data. So here we have used the automated end member extraction technique, and we extracted end members from this. After extraction of end member, we tried to classify the data of Kolkata region, and you see here we are able to classify different urban materials more clearly with the help of abundance images generated from the unmixing output, and then we applied rule based classification to get this kind of classification. So coming to the software, so there are plenty of softwares available for classification. NV, ADAS Imagine, Multispec, BIM, and Abhyas. So NV is one of the commercial software which is having full-fledged hyperspectral data processing module. ADAS is also having hyperspectral module. Abhyas is one of the open source software developed by our ISRO, and with the help of this Abhyas software, many of the data processing thing which I explained to you can be done, or it is possible through that. Now coming to the limitations of hyperspectral data. Normally what happens is sometimes fine atmospheric absorption features may be confused with the ground material being imaged. Data volume, you can say, Everest is 40 times heavier than your Landsat thematic mapper. So you see the data is very heavy. Redundancy, as I told, that there are some times overlap of information content over several bands, because I told VNIR and SWIR are two different detectors which is used for collecting data, and VNIR last range of the bands and short wave infrared initial range of bands are actually overlapping. So data redundancy is also there. So these are few of the limitations of hyperspectral data. So thank you everyone.